So today what we're going to do is we're going to do a comprehensive overview of electrochemical cells. We're going to look at a specific electrochemical cell. This one is a copper zinc electrochemical cell. The overview we're going to do is going to cover the following 7 things. And in particular, if you are studying for Achievement Standard 91393, demonstrate the understanding of oxidation reduction processes, this will be half of the report you'll have to write for this standard. So the 7 things, if I want a comprehensive overview of this galvanic cell, we can see on the left, notice that there are 2 half cells joined by a salt bridge in the middle, and there are 2 electrodes, a copper electrode on the left and a zinc electrode on the right. So 7 things I want to do to fully comprehensively explain this galvanic cell or this electrochemical cell is the following. I want to use the redox potentials at the top to identify the oxidation and the reduction half equations. I want to link what I observe in this cell, what will be observed in the cell, to the reactions that are happening. That's the oxidation reduction reactions. I want to justify what has been reduced and what has been oxidized by using the loss or gain of electrons. I want to also be able to justify what has been oxidized or reduced by using oxidation states or oxidation numbers. I want to be able to write these the half equations. I want to balance them correctly and then put them together to write a full oxidation reduction balanced equation. I want to be able to calculate what would be the voltage produced if I set up this galvanic cell. What is the E cell that is produced? And finally, I want to make or explain links. I want to write all of this. I want to link all these 6 points together. So let's look in detail at this galvanic cell here. This is a copper zinc cell. Now, this copper zinc cell, we are looking at it with the copper electrode on the left and the zinc electrode on the right. We could easily look from the other side, from behind, and it would have the zinc on the left and the copper on the right. So it's not important which side each of these on. Often people will put the reduction half equation on the right hand side, but in this case it's not, and it's not always. Notice when we have this galvanic cell, I have identified and given labels to the 2 different electrodes. I've drawn the salt bridge, which will help balance the charge across the 2 half cells. Okay, I've put a voltmeter here. Often at times we'll put a wee resistor in series with this voltmeter, but I haven't here. The solution, the electrolyte solution on the left hand side, is copper sulfate. Now what that means is this solution contains copper 2+ ions and sulfate 2- ions. This is an ionic solution here. And on the right hand side we have a solution of zinc nitrate, zinc 2+ ions and nitrate ions. So in the first instance, we are going to look at these 2 electrodes and we work out which one is going to be the reduction. Which one is, so we have these, 2 electrodes. There are these 2 redox couples that I've given, and I'm given the redox potentials for them. Okay, well, so for each of these half cells, they are always written from that the 2 species are being reduced. So here the copper 2+ is going to copper and zinc 2+ is going to zinc. However, when we work out the 2 half equations that these reactions will undergo, one will go forwards and one will go backwards. How do I know which one will go forwards? Well, pretty straightforward. The redox couple that goes as it's written is the one that is the most positive. And in this case, the most positive reduction potential is plus 0.34, or the copper 2 plus copper. So I can now write this half equation. It'll be a reduction half equation because it's going to be, if it comes straight from the redox couple and it's going the same way as we wrote it, it will be reduction. So here it is. Copper 2+ goes to copper solid. Copper 2+ aqueous because it's dissolved in solution, right? Now they don't tell us necessarily the states here, but we can see from this galvanic cell that the copper is a solid because it's a solid electrode, and so the copper atom as a solid, and we can see that the copper ions here are dissolved in a solution. They're aqueous, so we're going to put AQ here. Now, because I put the copper ions on the left and the copper solid on the right, the charges are imbalanced, right? So if I was to balance this equation, remember I have to balance the atoms that aren't oxygen or hydrogen first, then I balance the oxygens by adding water, the hydrogens by adding hydrogen ions or H plus ions, and then the electrons by the charge by adding electrons. To balance the charge and make it the 0 on both sides here, I needed to add 2 electrons to the left. Okay, so now we have drawn this reaction that's happening on the left hand side here. We need to justify why this is oxidation or reduction. This is actually reduction here, and the reason it's reduction is because each of these copper 2 plus ions is gaining 2 electrons, and when you gain electrons, when the electrons are on the left, it is a reduction. Okay, so the copper 2 plus is gaining 2 electrons. Now, if I'm doing the standard, achievement standard 91393, they want me to say exactly the number of electrons that are required for each one of the species we're talking about. So here we say that 2 electrons are each copper 2 plus ion gains 2 electrons to become copper solid. And I'm going to link this to what I observe. That means that this copper solid that's been made from these copper 2 plus ions will be deposited on this cathode. Now, interestingly, because it's been reduced, this is called the cathode. The cathode is always the electrode where reduction happens. So the mass of this copper electrode will increase. So if I was to measure its mass before this was set up and after it was set up, it would get larger because the copper ions have gained 2 electrons each and turned into copper solid that then is deposited on the electrode. So that's one explanation on how I know that this is reduction, because the copper 2 plus ions are gaining 2 electrons each. I can also talk about the oxidation number. What is happening to the oxidation number of the copper atom across this reaction? So on the left hand side, because this is an ion that has a charge of 2 plus, or a monatomic ion, the oxidation number of copper is +2. On the right hand side, because this is an element, an atom with no charge, a particle that's just one type of atom with no charge, its oxidation number is 0. So we can see that the oxidation number has decreased across this reaction, okay, across the arrow. It's gone from 2 to 0. So we would say that the copper 2 plus ion is reduced as the oxidation number of the copper atom in each of these has changed from +2 when it's in copper 2 plus to 0 when it's in copper solid. Also, we would observe that this blue solution here, this is produced by the copper 2 plus ions, it will become less blue as the reaction proceeds because the concentration of ions will decrease. Okay, so if this is the reduction equation, and this is the couple going forwards, the other couple has to be written backwards. So I go from copper 2 plus to copper. For the most positive one, the most negative one goes in the reverse reaction, so it goes from zinc to zinc 2 plus. To balance this half equation, the zinc atoms are already balanced. There's no oxygen or hydrogens. I just need to balance the charge, and I need to add 2 electrons to the right to balance the zinc 2 plus. This is my fully balanced half equation for my oxidation. How do I know it's oxidation? Well, I'm going to justify that. Zinc solid here is reduced because each zinc solid loses, see how these electrons are on the right, they've been lost, each zinc solid loses 2 electrons. And they're actually lost to the anode here. What actually happens is the zinc metal turns into zinc ions. It gives 2 electrons that travel through the wire, through the voltmeter, back to the copper, and those 2 electrons are given to the copper ions to turn the copper ions into copper metal. That's how this full galvanic cell works. Anyway, let's go back to this. Zinc solid is reduced as each zinc solid loses 2 electrons to the anode to become zinc 2 plus. Of course, because we're losing zinc solid and it's turning into zinc ions that will go in the solution, the mass of the zinc electrode will decrease. Okay, so I've justified why this reduction is reduction using loss of electrons, but I can also justify it using oxidation numbers. Zinc solid has a 0 oxidation number because it is an element. Zinc ion 2+, monatomic ion, its oxidation number is equal to its charge, +2. So here we can say that the zinc solid here is oxidized as the oxidation number of the zinc atom increases from 0 in zinc to +2 in zinc ion. 0 in zinc solid to +2 in zinc ion. Oh, let's go back to the start here. I said before that this was reduced. That's not right. It's oxidized because it loses 2 electrons, right? So this is oxidized as it loses 2 electrons. Loss of electrons, oxidation. Gain of electrons, reduction. Leo, the lion goes grr. So, okay, we've now explained the first 3 points that we needed to explain. Let's look at the next slide. And the next slide is going to be looking at, okay, I know the 2 half equations. Can I write a fully balanced equation? So here's my reduction half equation, and here's my oxidation half equation. Notice that I'm going to add these together, and I'm going to write the full equation for the reaction that's happening. Now, because I'm going to add these 2 equations together, I'm allowed to cancel out things that appear on opposite sides of the arrow. So notice here I have 2 electrons on the left here and 2 electrons on the right. I'm going to cancel them out, and then I'm going to write a full equation with all of the species in it. So I get copper 2+ plus zinc goes to copper plus zinc 2+. This is a fully balanced equation, and if I'm doing my achievement standard 91393, I need to have this fully balanced equation to get my excellence. Okay, so once I've done this, cool, I've balanced my equation, I've justified oxidation reduction on my previous slide, I have linked the reactions to the observations. So now what I want to do is calculate the E cell. What is the voltage produced by this cell? Now the E cell can be calculated by taking the right hand electrode reduction potential and subtracting the left hand electrode potential from it. So the right hand one here is zinc. Okay, so we're getting negative 70.76 minus the the left hand electrode, which is the copper one, which is 0.34. And if we carry out this calculation, we get an E value of minus 1.10 volts. Now don't worry if this is negative or if it's positive. No matter what happens, this reaction happens spontaneous. This is only negative because we are viewing this reaction from the front. If we viewed this reaction from behind, then we would have the electrodes on opposite sides and we would get a positive value. Now, because this E cell is negative, it means that the flow of electrons goes from right to left. So the electrons go from the zinc electrode through to the copper electrode. If this was positive, the electrons would flow from left to right. The reaction is spontaneous, no matter how, whether we put the half cell copper one on the left or on the right, it's always spontaneous. It's just the direction of the electrons that change. And that means electrical energy is being produced, and it's being produced at 1.10 volts. And that's the end of what we need to write down about a galvanic cell. I hope this has been helpful. Good luck with your studies.